Hello everyone and welcome to our course Design and Analysis of Algorithm, and this is our first lecture and our topic is Mathematical Analysis of Algorithms. So in this course there's a lot of mathematical terms and algorithms and logical theories which you need to understand properly. So I would highly suggest to go through all the lectures and watch all the recorded lectures, and don't skip any lecture because you won't be able to understand that later. And my office hours are Fridays. You can email me and we can have Zoom meeting if you need any help for your homework, exams, or any other things. But besides that, you can also email me and we can schedule another time for your meeting. So that's all I wanted to say. One more thing is whenever you will email me, I will try to reply as soon as possible. I would highly appreciate if you wait for my reply. Yeah, so let's get started. So today's lecture topics are asymptotic notation, which we will review, and then we'll review recurrences and solving recurrences like substitution method, recursion tree method, and master method. So let's start with asymptotic bounds. So we'll discuss the concept of asymptotic bounds in this slide, which is a fundamental tool in analyzing the performance of algorithms. These bounds help us understand how an algorithm's runtime or space usage grows relative to its input size. Now let's break it down into the three major notations. So first one is big O notation, represented as big OGN. It defines an upper bound for an algorithm's growth. It tells us the maximum time or space an algorithm will take even in the worst case scenario. For example, if an algorithm is big O n square, it means that its growth will not exceed n square as the input size grows. So second is big omega notation. It is written as omega gn, describes the lower bound. So this tells us the best case scenario for an algorithm. Well, it's useful when we want to guarantee that an algorithm takes at least a certain amount of time, no matter what. For instance, so big O omega n for a linear search means the algorithm will take at least linear time. Okay, third one is big theta notation. Theta gn represents the tight bound. So this is used when an algorithm's runtime is sandwiched between the upper and lower bounds. It grows at the same rate as gn. For example, theta n log n for a merge sort algorithm means it always takes n log n time regardless of input. So the key takeaways here is that big O is like a ceiling, big omega is the floor, and big theta is the actual growth rate when both the upper and lower bounds are the same. So these notations allow us to classify algorithms in terms of their efficiency, helping us to compare them more effectively. So let's now look at how we apply these asymptotic bounds to real functions. Here we have the expression 3x squared plus 2 equal to big O x squared. So here and we are analyzing it in terms of its growth rate. So first we see that 3x squared plus 2 equal to big O x squared. This is correct because the x squared term dominates the growth of the function as x becomes very large. the constant 2 becomes insignificant and the coefficient 3 is ignored in asymptotic analysis. Next is 3x square plus 2 equal to big O 3 cube, which is also true. Why it is true? Because x cube grows faster than x square. Therefore, x cube is an upper bound for this function, but it's not the tightest bound. Then finally, 3x square plus 2 equal to big O x naught. This is technically true as well because x naught or factorial growth, it's like a factorial if you're familiar with factorial, is much faster than x square. However, this is an even looser bound and far from being useful. So the key point here is that while all these statements are mathematically correct, the most useful bound is the tightest or closest one we can determine. For 3x square plus 2, the tightest bound is big O x square, first one, as it gives the most accurate representation of how this function grows. So this idea of finding the tightest bound is crucial in algorithm analysis because it helps us understand an algorithm's efficiency more precisely. Okay, now let's examine how to use big omega notation to describe the lower bounds of a function. Remember, big omega gives us the best case scenario or the minimum growth rate of a function. Here we have the expression 3x square plus 2 and we are analyzing it in terms of lower bounds. So the first one, which is 3x square plus 2 equal to x square, this is true because x square is the dominant term. As x grows, the constant 2 becomes negligible. So x square represents the minimum growth rate of this function. Second is 3x square plus 2 equal to omega x. Well, this is also correct, where x square grows faster than x, so x can serve as a valid lower bound. However, it's not the tightest lower bound. So third one is x square plus 2 equal to root over x. Again, this is a valid statement because x square grows much faster than root over x. However, this is an even looser bound and not very informative for analyzing the function. So the important takeaway here is that while all these statements are true, the most useful lower bound is the tightest one, which in this case is x square, the first one. It accurately reflects the minimum growth rate of 3x square plus 2. Okay, so let's talk about more about tight bounds. Like it represents the most precise characterization of a function's growth. When we have a tight bound, it means the function has the same upper and lower bounds. This is the case where we use big theta notation. So again, we have these two functions that we saw earlier, 3x square plus 2 omega x square and theta, big O x square. Now the first one is the lower bound, as we discussed earlier. X square represents the smallest growth rate for this function because 3x square dominates the constant 2 becomes negligible. Then second one, big O x square, this is the upper bound. Similarly, x square also represents the largest relevant growth rate since it dominates the function. Now when the upper and lower bounds are the same, we can conclude that the function has a tight bound represented as x square plus 2 equal to x square. So we can say theta x square. So when omega and big O, both of these functions are same, like if you see x square and x square both are same, so we can say theta x square, where we have x square plus 2 equal to theta x square. Now this tells us that the function's growth rate is tightly bounded by x square, and we won't have any other asymptotic bounds as tight as this one. So let's reflect on this question: why could we not have a second time bound? The reason is that the growth rate of a function is unique. Once we determine the tight bound, it fully describes the function growth behavior, and there's no room for another bound of the same precision. Okay. Alright, so well, while finding the tight bounds, it is often essential for analyzing algorithms. There are cases where determining the exact tight bound is very challenging or even impossible. So let's explore this idea through the example of the traveling salesperson problem. So the traveling salesperson problem is a classic optimization problem where we need to find the shortest possible route that visits a set of cities exactly once and returns to the starting point. The challenge lies in the sheer number of possibilities. To solve the problem exactly, we would need to evaluate all possible paths in the graph. For here for n cities, let's say we have n cities. This means analyzing n factorial permutations, an extremely large number even for relatively small n. This gives us a solution with factorial time complexity, which is very expensive. Now so here in this next slide we'll see the one I just said. The algorithm has a time complexity of n factorial, where n factorial represent the factorial growth of the input size n. This means that for this specific algorithm, the tight bound is n factorial. However, here's an important question: is n factorial bound tight for all possible algorithms? So we do not definitely know that, because there may exist a yet undiscovered algorithm with a fundamentally better complexity. For example, if someone were to find a polynomial time solution for the traveling salesperson problem, it would drastically alter the bounds we associate with this problem. So that being said, the problem itself is no harder than big O n factorial, meaning n factorial represents the absolute worst case scenario for any algorithm solving it. If someone develops an algorithm with complexity big O n n to the power n, which grows slower than n factorial, it may still not be very useful if significantly more efficient algorithms already exist. So the key takeaway is that understanding the upper and lower bounds of a problem helps guide us in designing better algorithms. But identifying whether a bound is tight depends on the state of research and whether there's room for improvement in our algorithms. Okay, let's now discuss positive functions and their importance in asymptotic analysis. The goal here is to simplify our expressions while ensuring we are staying accurate and mathematically consistent. Um, Here at the top we see the expression here gx equal to theta x square plus theta x cube minus theta x cube. So um, initially it might seem that the subtraction cancels out x cube, leaving us with gx equal to x square, but it is not. There's a problem here. This overlooks the possibility that x cube dominates x square, meaning gx growth rate would actually be closer to x cube. To handle this correctly, we first simplified step by step. Instead of subtracting x cube, consider the growth rates individually. We rewrite gx as x square plus 2.5 x cube. So we are rewriting it the same function. We are rewriting it. Now, since x3 dominates x square as x grows, we combine the terms into the tightest bound, which is gx equal to x cube. So now gx equal to theta x cube. This result reflects the actual growth of gx and avoids the mistake of underestimating this behavior. So the key takeaway we can say when working with asymptotic bounds, always focus on positive contributions to the function growth. Subtracting can lead to errors if we don't carefully consider which terms dominate. And of course, stay positive both in math and in mindset. Okay, now let's take a moment to discuss recurrences using the Fibonacci series. So for example, we are using Fibonacci sequence. Recurrences play a vital role in computer science, especially in the analysis of recursive algorithms. The Fibonacci sequence is defined as f0 equal to 1 and f1 equal to 1. Now there are the base cases. These are the base cases which define the initial conditions of the sequence. For all n greater than or equal to 2, the sequence follows the recursive formula, which is fn equal to fn minus 1 plus n minus 2. This means that each term in the sequence is the sum of the two preceding terms. For example, it could be 2, then 3, then 5, then 8. Here, if you look at here, we have. So as you can see, the Fibonacci sequence grows quickly and its values are widely applicable in various areas of mathematics, nature, and computer algorithms. So here we're focusing on recurrences using function call notation. Is another example of recurrences. For this case, you'll notice that instead of subscripted variable, we express recurrences in a way that resembles function calls. So we define the base cases here as t0 equal to 1 and t1 equal to 1. This provides the starting point for our recurrence, similar to initializing variable in a recursive algorithm. So here for n is greater than equal to 2, we define the recursive relationship as tn equal to tn minus 1 and plus tn minus 2. This structure is exactly the same as the Fibonacci sequence we discussed earlier. The function tn depends on the two previous results, which is why recursion is a natural fit for this problem. So using function notation emphasizes how recursive calls work in programming. For instance, if we compute t5 here, the function will break it down into t4 plus t3 and then continue to expand t4 and t3 into smaller recursive calls until it reaches the base case. So this notation is useful because it directly reflects how recursion is implemented in code. Later in the course, we'll also see how to analyze these recurrences mathematically to understand their time complexity. Okay, now let's look at an example of recursion using this simple pseudocode. Here's the function. Function n, then if n is greater than 1, print n, then function n minus 3. Now how it works? So this function doesn't explicitly define a base case, but it indirectly relies on the condition n greater than 1. Once n less than or equal to 1, the recursive call stop. That means if n greater than 1 is false, it stops the recursion. Then so the function performs in two steps. First, it prints the value of n. If n is greater than 1, if this condition is true, then it prints the value of n. Then it calls itself with n minus 3. This is a recursive process where the function keeps reducing n by 3 in each call until it no longer satisfied the condition n greater than 1. Okay, so here, now that we have seen the pseudocode for the recursive function, let's analyze its behavior mathematically by identifying its recurrence relation. So if we break it down, we are analyzing the function n, which operates as follows. Like first we do the condition check. If n greater than 1, then it proceeds with the recursion. This operation has a constant time complexity of 1. Then printing n. The print statement is also a constant time operation 1. Then third one is recursive call. The function calls itself with n minus 3, which introduces the recurrence. Now, to express this function mathematically, we define Tn as the time taken to execute function n. So we can say Tn equal to Tn minus 3 plus 1. So this equation tells us that the time complexity of function n depends on the time to process function n minus 3 and the constant overhead from printing n and checking the condition. Now, how can we solve the recurrences? So to find the overall time complexity, we can repeatedly expand the recurrence, like start with Tn equal to Tn minus 3 plus 1, that the one we have, and then substitute like Tn minus 3 with Tn minus 6 plus 1. So it will be Tn minus 6 plus 1 plus 1. So we'll continue expanding until we have n minus 3k, which is less than or equal to 1, where the recursion will stop. Okay, now here so we are just we'll formalize what we have been discussing so far, like the concept of recurrence. So when analyzing recursive algorithm, the time complexity is often expressed in terms of the function itself, representing the recursive calls made by the algorithm. So here we'll say So basically, in summary, if we want to say, a recurrence is a mathematical way of expressing the runtime of a recursive function. It defines the time complexity Tn as a relationship between the time required for the recursive calls and the additional work done outside the recursive call. In this case, the first one is Tn minus 3 and the second one is theta 1. So this equation tells us that to compute Tn, we must first compute Tn minus 3, then add the constant time taken for the current function call. And this process continues until we reach a base case where no further recursion is needed. Okay, now there is another pseudocode. So here in this pseudocode, there is a base case. So if the length of the array A is 1, the function returns immediately. This base case runs in theta 1 time. Then recursive case, like we calculate the midpoint of the array, mid equal to a dot length, which is a constant time operation 1. The function checks whether a mid equal greater than a mid plus 1. Again, this is a constant time operation 1. Then based on the condition, the function makes a recursive call on either the left half, like a0 mid with size n by 2, or the right half, which is a mid a dot length with size n by 2. So only one of these recursive call is made per execution of the function. And the work done outside the recursion is like all operations, midpoint calculation, comparison. These are all constant time 1. And then the relation of recurrence is the time complexity of this algorithm is governed by the recurrence. We can write Tn equal to Tn by 2 plus theta 1. So this tells us that the recursive function processes a smaller input size n by 2 in each step. It adds constant time work at every level of recursion. So here is this is the same one we had in previous slide. This is the same one. So in solving the recurrence, like we can solve this using the recursion tree method or master theorem. At the first level, the work is done 1, and so yeah, and then at the second level, each recursive call splits into 2 smaller problems of size n by 4 um, with constant time overhead. This continues until the size of the sub-problem reaches 1. Okay. Now, here is a stumper. Like, let's take a closer look at this interesting recurrence. Tn equal to Tn n plus 1. This is quite unusual because most recurrences reduce the size of the problem with each step, like Tn minus 1 or Tn by 2. However, this one does the opposite. It increases the size of the input at each step. So what does this mean? So in practical terms, this recurrence suggests that solving Tn requires solving Tn plus 1, which in turn requires solving Tn plus 2, and so on. So the problem never shrinks, it grows larger in every step. So if the function is increasing, this leads to a critical observation, like there's no base case. Unlike typical recurrences, Tn doesn't terminate at a smaller input size. Instead, it keeps expanding indefinitely. As a result, the recurrence doesn't converge or stabilize at a solution. So um, the recursion, as I said, the recursion never ends. It effectively loops forever. The function does not converge to a base case or provide meaningful result. So, so why it's problematic? Um, we can see like well, in algorithm design and analysis, a well-formed recursive function should shrink the input size with every recursive call, and it should reach a base case where the recursion terminates, and it should ensure that the recurrence relation can be solved to provide a finite and meaningful result. So in this example, this violates these principles because each call leads to a larger input size and there's no base case to stop the recursion. So to make recursive algorithms analyzable and functional, we'll focus only on decreasing recurrences, those where the input size decreases with every step. For example, like Tn equal to Tn minus 1 plus 1, this kind of function. So we'll see some example here. These are some sample functions which only decreases. So such recurrences allow us to trace the steps back to a base case, solve the recurrence, and determine the algorithm's time complexity. So like I said, each recursive call is on a smaller input size. These are the examples. So these are more. So we'll focus upon these two types and mostly the second type. Why? Why focus on these two? Like we'll focus on linear decrease and fractional decrease. So linear decrease models problems solved incrementally, step by step, like sorting or searching in a sequential manner. And fractional decrease captures divide and conquer strategies where problems are split into smaller subproblems, such as in quicksort or merge sort. And both approaches guarantee that the input size decreases with each recursive call, and the recursion terminates when the input reaches a base case, and we can derive meaningful time complexities using methods like substitution, recursion trees, or master theorem. Okay, and let's talk about the essence of solving recurrences, which is the key skill in analyzing recursive algorithms. Now, here for instance, we have a function Tn equal to 3Tn by 2 plus 2. Now this means the algorithm divides the problem into 3 subproblems, each of size n by 2, and it does an additional constant amount of work plus 2 outside the recursive calls. So as you already saw some lot of examples in previous slides. Now we'll see the goal of solving a recurrence is to determine the asymptotic bound of the algorithm's complexity. So this involves finding the growth rate of Tn using big O, big omega, or big theta notation. So the solution is not a specific function like Tn equal to 7n square plus 1 plus 5, this kind of, but instead we are looking for the rate of growth or behavior of the function as n is infinity, such as tn equal to n log n or tn equal to n square. Now, why it's important? So, solving recurrences helps us predict how an algorithm will scale with input size, and it allows us to optimize algorithms by comparing different approaches and their growth rates. Okay, so um, what is the substitution method? So, it is like plugging in increasing values of n. We calculate tn step by step to observe how the function behaves as n grows, and identifying the pattern from the computed values. We aim to determine a non-recursive formula that represents tn, and thirdly, expressing tn in terms of n, because ultimately we derive a closed form expression or asymptotic bound for the recurrence. So why will use substitution? We'll use it because it's a straightforward step-by-step method, and it allows us to understand the growth rate of tn without requiring advanced tools, and it's an intuitive way to verify the correctness of more complex solutions. Okay, now if you don't have a good guess, like we'll see three steps here. First is explore the recurrence. Like if you don't have a good guess for the bound immediately, you can start by plugging in small values of n to compute tn for several steps. Look for patterns in how the function grows. This exploration can give you an idea of whether the function is growing in linearly, logarithmically, or quadratically. Um, Second is make a guess. Once you identify a potential growth rate, you can guess an upper, lower, or tight bound for the recurrences. We'll also see examples. And then third is prove the guess using induction. So now that you have a guess, you have to prove your guess which is correct or not by using mathematical induction. So it is an example here. So t1 equal to 1, and this is our base case indicating that the function terminates when n equal to 1. Then for n greater than or equal to 1, we have tn equal to 2tn by 2 plus n. This tells us the problem is divided into two subproblems, each of size n by 2. So there is an additional cost of n outside of the recursive call. Now here, first one will do make a guess. Here will form a guess here. So forming a guess based on the given values, the recurrence is t1 by 1, tn equal to 2tn by 2 plus n, where we'll compute tn for a few small values of n to identify a pattern. Then as I said, n equal to 1, we have the base case. Then for n equal to 2, using the recurrence. Then for n equal to 4, again using the recurrence. For n equal to 8, using the recurrence. For n equal to 16, and then we are continuing until 80 here. So now we are observing the pattern. If you try to observe the pattern here from this calculation, we notice that tn increases as n log n, which suggests tn equal to n log n. So we'll prove this guess formally in the next step using substitution or another method here. So in the previous step, we computed values for the recurrence. So if you look at here, we have the table to calculate until 80. Then like I said, we now observe the pattern Tn equal to n log n. So for your better understanding, we have this table. Now on step 2, we'll state the guess. Like now that we have analyzed the recurrence and observed a pattern, let's formally state our guess for the asymptotic bound of Tn. Now the guess is we have hypothesis that Tn equal to big O n log n. Now this means we believe the growth rate of Tn is at most proportional to n log n for large n. In other words, we are guessing Tn less than equal to c dot n log n, where for some constant c, this inequality will allow us to prove the bound rigorously in next step. So now that we have formed our guess and it's time to validate it formally through proof of induction, while we won't require you to perform this step on your own for now, I want you to see how this process works so you understand how to handle it when needed. So here we have base case induction, inductive hypothesis and inductive step, where in base case we have so first step is to verify that the recurrence holds for the smallest inputs, like check T1 by definition T1 equal to 1 and this aligns with our guess. Check T2, substituting it into the recurrence. Again, this matches our observation. By confirming these small cases, we establish the foundation for our proof. Second is inductive hypothesis. So assume the hypothesis is true for n equal to k. So this assumption allows us to prove the next step. Now prove that the hypothesis holds for n equal to k plus 1, substituting into the recurrence. So let's see here, that was the if we take the inductive step here, so let's say you are using this example. So the recurrence we are working with is 2Tn by 2 plus n. Now our goal is to prove that Tn is less than or equal to c dot n log n for some constant c. Now when we will apply the hypothesis here, it will be like Tn by 2 is less than or equal to c dot n by 2 log n by 2, and substitute this into the recurrence. Tn less than or equal to 2 dot, and then inside your parenthesis it will be c dot n by 2 log n by 2 plus n by inductive hypothesis. Now if we simplify this, so this is the expression we'll get after simplifying this. So we'll simplify this by multiplying the 2 through like here okay, this one. So you will see we have this using the logarithmic property, we have this log a by b log a minus log b, and now we can break it down, and then we can substitute back into the expression here. So now we have Tn less than or equal to c dot n log n minus c dot n log 2 plus 1, and this uses the logarithmetic property. Now here minus c dot n and plus n represent lower order terms compared to the dominant c dot n log n. So to simplify the log 2 term into a constant, this makes the equation easier to interpret and finalize. So the final observation at this stage, the c dot n log n term dominates for large n here. If you go here, so now we have the final simplified expression, which is Tn less than equal to c dot n log n minus c dot n plus n. So long as like to maintain our inductive hypothesis, the constant c must satisfy c greater than equal to 1. This ensures that the dominant term c dot n log n properly bounds the recurrence. Now, since our hypothesis holds for all n as long as c greater than or equal to 1, we can conclude that Tn belongs to big O n log n, and this successfully completes the proof. The tight bound we derived aligns with our original hypothesis and is consistent with the asymptotic complexity. Okay, now let's talk about the recursion tree method, a visual and structured way to analyze recursive algorithm. This method breaks down the recurrence into individual levels of recursive calls, making it easier to understand and solve. The first step is draw the tree. Like we'll draw the tree representing the recursive calls. Then we'll determine the cost of each level, determine the height of the tree, then express the total cost as a summation, solve the summation, and then if there is any example, so we'll have example and discussion coming next slide. Okay, now let's apply the recursion tree method to an example. We'll use the recurrence Tn equal to 2t n by 2 plus n, which is a common recurrence in divide and conquer algorithm. We just used it in our previous slide. So now we'll see it as a tree. Now first we draw the tree. In this tree, the root represents the first function call with input size n. At each level, the input is divided into two subproblems of size n by 2, and this division continues recursively, reducing the input size by half at each level. So if you look at here, the first one is n, then the second level we have n by 2, and the third level is n by 4. So the bottom level will be n by n, n by n. Okay, so number of levels here is log n. Now the total cost, each level costs n. There are log n levels, so big O n log n. Number of children, so here we have So each node will have a number of children equal to the number of recursive calls. So how many children of the root node for each? First we have Tn equal to T 2Tn by 2 plus T plus n. So each node will make two recursive calls to subproblems of size n here. So here each node will make two recursive calls to subproblems of size n by 2, and this creates a binary tree structure. For second one, 5t n by 3 plus n, it will have 5 recursive calls. And then for the third one, so this is more complex, with one branch focusing on a halved input n by 2 and 3 other branches working on smaller subproblems n minus 2. So the tree structure will be uneven, and said, it will be 4 more recursive call, resulting in 4 into 4 16 grandchildren. And on the previous ones, first one have 4 grandchildren and second one has 25 grandchildren. Okay, now we'll see master method, which is an essential tool for solving recurrences of the form Tn equal to at n by b plus fn. Now where we have conditions like a is greater than or equal to 1, this represents the number of subproblems the algorithm divides into at each recursive step. Then second condition is b is greater than 1. This specifies the factor by which the problem size is divided into in each step. Third is fn, which is a function that captures the cost of non-recursive work done at each level. So the master method provides us with a systematic way to determine bounds for such recurrences. Let's look at the next slide. Here we have an example of merge sort. So where we have condition a, b and fn. It fits, but how can we use it? So in master theorem, so here, as I said, we have these key elements in this function. We already saw it on the previous slide, where n by b is either the floor or ceiling, and the other a, b and fn is a given function, the conditions, and we have the function. Now here, then on this function has the following bounds, like if fn equal to big O n log b a minus e for some constant e greater than 0, then Tn equal to theta n log b a. And then it has the following bounds, like if fn equal to theta n log b a, then Tn equal to theta n log b a log n. Now here, when fn is dominated by the recursive term, where we have a if fn equal to big O n log b a minus e for some e greater than 0, then we can say Tn equal to theta n log b a. But when fn matches the growth of the recursive term, it is fn if fn equal to theta n log b a, then Tn equal to theta n log b a dot log n. And when fn dominates the recursive term, we have like if fn equal to omega n log b a plus e for some e belongs to e greater than 0, and if a dot f n by b less than or equal to c dot fn for c less than 1, then tn is equal to theta fn. So this is all written here. Well, here A determines the number of subproblems, as I already said. B determines the division factor for the input size, and Fn captures the non-recursive cost. Now, in the examples at the bottom of the slide, you will see here we have n square is compared with the recursion term, and for n cube by 4 square, the growth rate clearly dominates, highlighting case 3. Now to solve this problem, this smart sort example, we'll see here. A equal to 2, number of recursive calls, B equal to 2, division factor of the problem size, and Fn equal to theta n, non-recursive call. And then we'll compute log BA, so log 2 equal to 1. And on step 3 we'll compare fn with log n n to the power log ba equal to n to the power 1. Now we have 3 cases to consider here. On case 1, the recurrence fits this case, and Tn equal to theta n to the power log ba equal to theta n to the power 1. But here this function n, fn equal to n, which matches n to the power 1. And then on second case, if fn grows at the same rate as n log ba, the recurrence fits this case. This leads to an extra log n factor, and the result will be fn equal to n. On the third case, this applies when fn grows faster than n log ba, but it doesn't apply here since fn matches the growth of n to the power 1. So the final result is the recurrence satisfies case 2, and the solution is Tn equal to theta n log n here. So the second one is the solution. Okay, so this is the end of our first lecture. I know this might be a little bit complex for you to understand. That's why I said in the beginning that for any kind of help, please feel free to reach out to me. And I will also upload and add some extra resources where you can find some where you can learn more about these terms, and we'll have some more explanation. I will upload it with this lecture, weekly lecture in module. Thank you.